Good afternoon, everyone. My name is Takiwa Smith, founder and executive director of Science, Engineering, and Mathematics Link Incorporated, and I want to welcome you to our National Chemistry Week celebration. I have always loved math and science as a little girl, as long as I've known, and my favorite STEM discipline is chemistry. There is something about mixing chemicals, seeing things blow up, seeing reactions, that is exciting. And so from day one, we have always celebrated National Chemistry Week. And as you can see, my t-shirt has all the things that chemists have: goggles, flasks, graduated cylinders, test tubes. And so although we weren't able to have an in-person chemistry week, we wanted to make sure that we still engaged you in fun chemistry activities and introduce you to the fun world of chemistry. So hopefully you will get an opportunity to see some hands-on demos that spark your interest in chemistry, interact on the chat with our chemists that are doing interactive demos. We actually are going to play a fun game of chemistry Jeopardy. And at the end of the day, whoever is most engaged in the chat will get an opportunity to win a fun prize, which we'll announce at the end of the day. So have a great day of chemistry. We're going to have some fun as we celebrate National Chemistry Week. So I am about to show a short video that introduced you to what chemistry is all about. Wait, okay. Let me come back. It'll be great if I could share my screen. Sorry about that. So SCM Link cannot do our work without amazing partners. So we are so excited to host our National Chemistry Week in partnership with two of our Metro Atlanta community partners, the Rho Phi Lambda chapter of Alpha Phi Alpha Fraternity Incorporated and the National Coalition of 100 Black Women Northwest Georgia chapter. And so before we get started, we're going to have greetings from each of these chapter presidents. So right now, I'm going to bring in Mr. James Weber, the president of Alpha Phi Alpha Rho Phi Lambda chapter.
Okay, can you hear me okay?
We can hear you okay.
Okay, great. So good afternoon. On behalf of the Brothers of Alpha Phi Alpha Fraternity Incorporated, Rho Phi Lambda chapter, I do bring you greetings. My name is James Weber, the president of the Rho Phi Lambda chapter. So Alpha Phi Alpha, the first intercollegiate Black fraternity founded for Black young men on the campus of Cornell University, has always been an advocate for education, and especially STEM research and education type fields. So with prominent members like Garrett Morgan, the inventor of the first traffic light, and who also owns the first patent for the gas mask, or Commander Winston Smith, who is a prominent physician, scientist, and a NASA astronaut, we have always taken the role of STEM research as a vital part of our community and our country. So we're very excited to be partnering with SimLink and with 100 Black Women of Northwest Georgia to bring you this program. So again, we hope that you find it informative and that it continues to spark the interest of STEM-related activities and education. And again, to SimLink and 100 Black Women of Northwest Georgia, we thank you for allowing us to partner with you all.
Thank you so much. We're so excited. And one of your chapter members will actually be our first speaker doing some great chemistry activities. So
Yes.
Thank you so much for your partnership.
Thank you.
And now we will hear from Ms. Kelly Humphrey, the president of the 100 Black Women, National Coalition of 100 Black Women Northwest Georgia chapter.
Good afternoon. I bring you greetings from the Northwest Georgia chapter of the National Coalition of 100 Black Women. My name is Kelly Humphrey, and we are delighted to participate in SEM Link's National Chemistry Week event in support of our chapter member, Takiwa Smith. As an organization, the National Coalition of 100 Black Women is committed to focusing on advocacy issues that impact the health, education, economic empowerment, leadership development, and gender equity for Black women and girls. One of our major advocacy initiatives is STEM education. Therefore, this event aligns with our organization's mission. Again, thank you for including us and allowing us to collaborate with you on this event. And thank you all for participating in what I am sure will be a wonderful educational experience.
Thank you so much. We're so excited. And thank you so much for your support. So have a great rest of your day. So before we get started, we're going to bring our first person on shortly. I want to ask how many of you like chemistry? Just put in the chat how many of you like chemistry and what is your favorite chemistry experiment or favorite chemistry TV show or favorite commercial. So for me, I'm going to share my favorite regular commercial that has chemistry. So do you all remember the Allstate Mayhem commercials? How there's so many Mayhem commercials, like so many things that go wrong, which is why they try to convince us to keep paying our insurance premiums, right? So my favorite Mayhem commercial, which many of you all may not realize is chemistry, is the commercial where they're tailgating and they put the grill back in the truck when they go in the game, and then it goes boom. Can any of you think why it goes boom and why the truck blows up, or why they should have left the grill outside to cool off? You can share in the comments. One of the things it's important for one of the things that when you think about chemistry experiments and what make things explode, there are two things that are super important: temperature and pressure. And if the temperature and pressure are off, that makes things go boom. So in that commercial, I understand, they probably didn't want to keep their grill outside the truck because they may have came back from the game and it didn't, it would not have been there. But it would have been better for them to let it cool off, because once they put it in the truck, the temperature and the pressure caused that explosion, which is the mayhem, which means they had to call their Allstate agent. So without further ado, I am going to bring in our first chemist of the day. Dr. Tedrick Campbell, who is a member of our community partner Alpha Phi Alpha chapter. Um, Tedrick, Dr. Campbell is a physical chemist, right, Dr. Campbell?
That's correct.
Physical chemist. So I am going to come out and go ahead and let you do your thing, Dr. Campbell. You ready?
All right. Thank you, Ms. Mill.
You're welcome.
Hello, everyone. My name is Dr. Ted Campbell, and I'm here with my two young chemists, my sons here. One is Adrian. Say hello, Adrian.
Hi.
All right. And the other one is Andrew. So say hello, Andrew.
Hi.
All right. So, guys, I have a question. What is the coolest thing about fireworks?
The boom.
The boom. All right. That's great. Andrew, what about you?
The little dots of color.
The color. All right. Awesome. So, the one thing about fireworks, of course, is the boom, right? The boom, of course, comes from gunpowder. We would definitely not be doing any boom right now, all right? But the other parts about fireworks, of course, are the colors. And all the colors come from chemistry. You guys know that?
Mm-hmm.
All right, great. All right. So just in general here, come on, Tiffany. I have another sister here, my daughter. Oh, Tiffany. Over here, guys. All right, Tiffany here. All right. So I have a board here. I'm gonna kind of talk through exactly what goes on in terms of the chemistry of fireworks. So in the periodic table, you have a left side and you have a right side in general. The left side are made up of metals. The right side is made up of non-metals. So when a metal and a non-metal combine, they form what's called an ionic bond. All right. So it's called an ionic bond. All right. So what you guys hear me say a lot is about compounds. So when I say the word compound, it really means that it is an ionic bond, a bond between a metal and a non-metal. And just go a little bit further. So take any element from the left side. Let's take calcium. Of course, the symbol for calcium, you guys know. The symbol for calcium is Ca. All right. As an ion, as an ion, calcium has a 2 plus charge. All right. So this is the metal or the cation of the ionic bond. Of course, this combines again with a non-metal, and we'll take any random non-metal. We'll take chlorine. Chlorine, of course, the Cl, has a negative charge. Well, when you combine the calcium and the chlorine as an ionic bond, the form becomes now CaCl2, and now I have an ionic bond, i.e., now I have a compound. Okay, so here's called calcium chloride. So why is it important? Oftentimes, when you come to having compounds and fireworks, it's not the actual metal; it's more or less a compound. So it has some parts of a metal and some parts of a non-metal, again forming the ionic compound. But much like baking a cake, there's always one main part. So, for instance, if you were baking a strawberry cake, obviously you have strawberries, you have eggs, you have flour, so forth and so on. But the part everyone talks about is the strawberries, i.e., that is the main part. So, as we go through trying to demonstrate the chemistry of fireworks, the main part here is the metal, that is the cation. Again, in the fireworks, it comes as a compound, so it does have another anion with it, but the main part, if you will be the metal. All right. So here I'm going to list just the cations here that we are going to test here on today. And so my sons again, the chemists, again, say hi guys.
Hi.
All right. They are going to be representing um, what you guys will see at home, and they'll be telling me the colors they see from the various metals. Okay. So, of course, guys, all right. Don't do this at home. All right. Be very careful. This does involve fire, which of course my kids love. So we have a torch here. A flame here. So, just so we understand how like wood burns, of course. So if I have just some wood here and it burns, I get just a general orange flame. All right, no big deal.
Can I hold it?
So the first compound or the first cation we're going to test is barium. All right, the symbol for barium here is Ba. Okay, guys.
Okay.
So what I want you to tell me here is the first color you guys see. Again, not the wood burning, but the first color you see. You ready? You see the color at all? No.
Why are you doing upside
What do you see?
White.
No, look closer. What color you see?
Green.
Green. All right. Good job, guys. So in fireworks, all right, the color that comes from green is made up of barium. All right. So come here again. Green for barium. Again, it has barium again has a green color.
Adrian.
All right. Going on. Now we're gonna go on to the next metal here. The next metal here we're gonna test will be lithium. Again, guys, all right, these are compounds, all right, not the actual metal. These are compounds. So again, we're gonna test Li here, which stands for lithium. All right, come here, Andrew. I'm gonna hold it here. All right, good job. You're holding it well. All right. So again, guys, all right, this cup out here is lithium. Now, Andrew, again, as you hold it, would you tell me the first color you see come off, okay?
Okay.
You guys see this at home? What color you see, Andrew?
I see red.
You guys see this at home? All right. So that should be red. All right. So thank you, Andrew. So let's probably leave that. Oh, it's fine. So lithium forms a red color. All right. The next metal we're going to test now is SR. You don't want to know what SR stands for? Come here, Adrian. Okay, guys, anyone know what SR stands for? SR, of course, stands for strontium. All right. So, Adrian, again, all right. Once I light it here, you want to tell me the first color that comes off, okay?
Okay.
And guys, again, right, for you guys at home, all right, these are the compounds, again, that makes up fireworks, again. So all fireworks have a main cation, all right? The cation, again, it was carry the colors of the flame. So come on top here again. Come down some measure. Down, right there. Cool, you see, Adrian?
I see orange. No, reddish.
All right. So the first one he said was orange. Then he said reddish. All right. So oftentimes the strontium carries more or less of a deeper red, almost a magenta, a purple-like color. All right. So we would say deep red here or either magenta. So we say deep red. All right. The last compound here we're going to test is calcium. Again, so again, the main part here is a calcium. I'm sorry, that's sodium. All right. You can come again, Andrew.
Okay.
All right, you hold it there. All right. So here now again, we want to test now sodium. And again, Andrew, all right, the first color you see come off, tell me that color, okay? So again, guys, this is sodium in Na.
Orange. I see orange.
All right. So that's can I see the way at home. All right, but he's saying orange. All right, and that's correct. Sodium gives the orange color that we all see in fireworks. Right. So guys, again, right. The first four items here that we did, again, these were all compounds, i.e., these were all some type of ionic bond. You had barium, it gave a green color. You had lithium, it gave a red color. You had strontium, which gave a deeper red color, almost magenta. Then we had sodium here, we gave a orange color. All right. Now, again, we don't have any gunpowder, but the one thing that I think Andrew mentioned was that the sparkles. All right. There's one main compound that kind of makes things light up very, very, very bright. All right. And that one, you guys know?
Yes, I remember it, but I have forgot the name.
I'll say it again, Andrew.
I forgot the name.
All right. So the name of that compound or name actually of that metal is magnesium.
Oh yeah, magnesium.
All right. That is magnesium. All right. So earlier I mentioned, right, that we had on the compounds here. Here for MG, we're going to test the actual magnesium ribbon. All right. So this is a metal again from group 2 of the periodic table. All right. And so here we go, guys. Let's do it. All right, no, I have it here. All right. So we have here some tongues, and inside the tongues here is a piece of magnesium ribbon. All right. So let's see now what happens when you actually go to excite a piece of magnesium ribbon.
You have to put it on the top of fire.
So you hold it tight, okay, Andrew?
Yes. I know how to put it at the top. That's right.
And we're gonna do this twice, okay? So here we go. The first pass here, guys. Again, this is actual magnesium ribbon. This is an actual metal.
Not working.
There.
A little.
See that?
Wow.
All right. Adrian is excited again. All right. Let me do it again. Let Adrian hold it. All right, once again, grab here with the tongs. Being shown here. You can hold it here, Adrian. Hold it tight. We're going to side it again here. All right. So, guys, oftentimes you'll find magnesium in sparkles and a number of different items. All right. So you can imagine combining several metals to get the bright light and as well as the colors. All right, guys. All right. So I want to thank, of course, Adrian Tiffin again for helping me out. All right. If there are any questions whatsoever, feel free to reach out to me. All right. Thank you, guys. All right. Have a good day.
What was that white smoke?
The white smoke was the magnesium ribbon. So all of the other ones show colors. The barium, the lithium, the strontium, the sodium, they all give you the various colors and fireworks. The magnesium is the one that gives you the big bright white light, the big spark, if you will.
So whenever there's fireworks, if there's white, we see magnesium.
Generally speaking,
If
that is
there's
magnesium. Aluminum can also do the same thing. Now depends on cost, depending on the type of show. It could be various metals, but in general, the big bright white light is magnesium.
Okay, one more question, and I'm going to see if anybody has a question in the chat. So you had said about the metals, which are on the left side of the periodic table. I should know that, right? They're on the left. No, they're on the right side, right?
The metals are will be on the left side of the periodic table.
Left side. I ain't looked at one in a minute. Um, why are metals good for the reactions for fireworks? Like, why metals? Why not gases?
Well, metals again, they are highly reactive. So if you remember the properties of the metals in general, so if you look at a group 1 metal, for instance, I mentioned lithium. So you notice that I always had these compounds. That because in their rest state they are very, very, very reactive. However, though, if you can combine them with an anion, they can be less reactive, if you will. They become stable. Then they of course can always be excited. Talk about gases. If you look at group 8A on the periodic table, these are called noble gases. Why are they called noble gases? Because these things are non-reactive. They don't react. So in a very general sense, metals are high reactive, and your non-metals are.
Okay, you said cations and anions.
That's correct.
What are those? Because I'm like, what? Okay.
Fair enough. So again, right. So for the students at home, and I try best to kind of put it in terms of a cake. If I do a strawberry cake, strawberry is the main part, right? But the strawberries are combined with various items. So if you will, the strawberries act as a cation because it is the main part, if you will, and all the other stuff acts as the anion. So in terms of chemistry, the cations are metals. So when metals go from being an elemental atom to being an ion, they become what's called a cation, has a positive charge. Non-metals go from being a non-metal as an atom to an anion having a negative charge. When you combine the positive cation with the negative anion, you have a then called a compound, and that compound is indeed stable.
Okay, so pretty much fireworks are just a big reaction that goes boom that we're seeing.
Fireworks are mainly two things. All right, gunpowder, that's the boom, and some type of ionic compound, generally speaking. All right, and you would know the type of ionic compound based upon the color you guys see.
Okay. Wow, thank you. I mean, chemistry is truly everywhere, but I never really thought about fireworks, right? Because you just hear them go boom and you watch the pretty colors in the sky.
That's correct. No one thinks that took a chemist to develop this.
Well, we're going to just check. Can you hang on like 1 second to make sure there's no questions in the chat before you go? Are there any questions? I don't see any question in the chat, but we will come back
Yeah,
and let you know if we are.
I have a one here. Someone.
Wait, you went away. Okay.
Hello. See me now?
Yes. Yeah, I see you now.
Yeah. So someone mentioned here that they didn't hear a boom. That's correct. Again, we didn't have any gunpowder. That would have been too dangerous, especially here. But the point was to demonstrate where the colors came from.
So so if we want, well, okay, we cannot do the gunpowder at home, right? Like
That's
that's
correct.
only for professional
Please,
fireworks people.
that's correct.
So the gunpowder brings, okay, let me not ask this question because some will try it at home and we can't. So pretty much if you want to try it at home, you cannot do anything with the gunpowder. Keep that to professional
Yes,
fireworks.
please. All right.
People.
Never try to take gunpowder and try to put a fire to it. Even small amounts would cause a very big explosion. Let's not do that, please.
Thank you. And why do you have goggles on with this experiment?
So it's very important, right? In terms of labware, your eyes are one of your most critical parts. You should always be covered head to toe. Depending, because this was a relatively dry experiment. I don't wear a lab coat, but regardless of what's going on, I always wear goggles. Your eyes are very important.
Well, thank you so much, Dr. Campbell. I love fireworks, so that was really, really cool. Even as a chemical engineer, I didn't make the connection that fireworks are actually a reaction between metals. All right. So I don't think we have any questions. Thank you so much and enjoy the rest of your day. And I'm so happy that those trees didn't catch on fire. And tell your future scientists, thank you for helping.
All right. Say bye, guys.
Bye. Bye.
Bye. Okay.
All right. Thank you.
You're welcome. That was so cool. I mean, I'm a chemical engineer and I didn't even realize that fireworks are a reaction. So chemistry is truly everywhere. So we're going to have our next demonstration, Kids for Chemistry, from Mr. Gerald Baldock. I'm going to let him in right now.
Okay.
Good afternoon. How are you?
I'm just
Thank
fine.
you so much. So tell us a little bit about your org, what you do, and then let me know when it's time to share your screen so we can get to your activities. We appreciate you so much for being a part of our Chemistry Week celebration.
I'm so glad to be here. Can you hear me just fine? Can you hear me okay?
Yeah, I think we can hear you just fine.
Okay, great. Okay, so my name is Gerald Baldock, and me and my sons, we have a program called Kids for Chemistry. All right, I'm a chemical engineer, and all my sons, I have 3 sons, and they are all chemical engineers also. Well, one is a computer engineer, but that's close enough, okay? And we started a program when they were little, when they were just kids, called Kids for Chemistry. And they went around teaching other kids chemistry. So what we did in the last year is we started making animated videos of them as they were kids. And now we have these videos where we have the characters named after my sons, and we have some other characters, some young ladies. Awa is one of the main characters. Maki is another main character. But in any case, they are now teaching the first 20 atoms of the periodic table. And we have some exciting videos for you. And what I like to do is actually start off with one of the videos. Let me show you one. And then we'll come back and we'll have some more questions about it, okay? So here we go. And please, if you have a hard time hearing it, let me know, because it's important that you can hear this, okay? So this is the first video.
What do you want to be when you grow up?
I want to be a chemist. How about you? What do you want to be?
I want to be a chemical engineer.
What is the difference?
Well, they work close together, but chemists usually work on chemical reaction.
Okay, what happened?
In a lab and on a small scale. They try to determine the important properties of the reaction to make the products. And chemical engineers work on the same reactions, but in the plant and on a large scale. They try to make the products in large quantities and safely.
Oh, so that's the difference.
Yup. But do you want to know the most important difference between chemists and chemical engineers?
Yes. What is the most important difference between chemists and chemical engineers?
Well, chemical engineers are better looking.
Really? Well, I want to be a chemical engineer also.
Nah, I think you look more like a chemist.
Hey!
I'm just joking. Wow, it looks like it's going to start raining. We better go inside before we get wet. So, Awan, the atomic number tells you how many protons and electrons are in an atom. Is that right?
That's right, Gerald.
Well, what about the neutrons?
The neutrons don't always match the atomic number. In this lesson, we are going to go over the lithium atom. Lithium is number 3 on the periodic table. It has 3 protons and 3 electrons, but it has 4 neutrons.
But before we talk about lithium, let's review the hydrogen atom and the helium atom. Orbital, where are you?
I'm coming. Give me a moment.
There you are. Can you show us the hydrogen atom again?
Of course I can. This is the hydrogen atom. And as you can see, hydrogen has 1 proton and 1 electron. That's why hydrogen is number 1 on the periodic table.
And if you look at the periodic table for hydrogen, it has the number 1 on it. This number is called the atomic number.
Orbital, can you show us the helium atom now? Why, certainly. This is the helium atom. It has 2 protons, 2 electrons, and 2 neutrons. That is why it is the second atom on the periodic table, because it has 2 of each.
And if you look on the periodic table for helium, it has the atomic number of 2.
Remember that the red circle represents the s orbital. S orbitals are round and spherical, and both electrons are in this orbital. We have a special name for this orbital. We will call it the 1s orbital, since it is the first s orbital. You must remember that the maximum number of electrons that can go into an orbital is 2. This is very important to remember because lithium has 3 electrons. I want everyone to know that I am putting numbers next to the protons and neutrons so that my nose does not get too big. My face will start to get cluttered if I try to put all those protons and neutrons in my face.
Orbital, show us the lithium atom now.
This is the lithium atom. It has 3 protons and 3 electrons. And you must notice that it has 4 neutrons.
Lithium is number 3 on the periodic table because it has 3 protons and 3 electrons. If all of the atoms on the periodic table follow this trend, the number of protons and the number of electrons will always match the atomic number.
Remember that I told you that the number of neutrons does not always match the atomic number. Hydrogen and lithium are examples that show this.
That's a shame, because if the neutrons match the atomic number, then it would be so easy to remember. We could say that the atomic number tells you how many protons, electrons, and neutrons are in an atom.
Well, it's still easy to remember. The atomic number tells you how many protons and electrons are in an atom. You just have to remember that the number of neutrons can be different from the atomic number.
It is really easy to remember. The first atom has 1 proton and 1 electron. The second atom has 2 protons and 2 electrons. The third atom has 3 protons and 3 electrons, and so on.
Did you notice something else about lithium? Look at the third electron.
Yes, I did. The third electron is on another orbital, a new orbital that was formed because the maximum number of electrons that can be in an orbital is 2.
That's right. A new orbital is formed, and it is another s orbital. And notice that it is a bigger s orbital. What do you think we should call this new s orbital?
Well, the first s orbital is called the 1s orbital. So the second s orbital must be called the 2s orbital.
That's absolutely right.
Now you know the structure of the lithium atom. It has 3 protons, 3 electrons, and 4 neutrons. It has the 1s orbital with 2 electrons, and it has the 2s orbital with 1 electron.
Hey guys, I'm here to get my lithium earrings.
Oh yeah, we almost forgot about you. Here they are.
Go ahead and try them on.
How do they look on me, guys?
They look really good on you, and I'm really jealous.
Well, thanks guys. These earrings are a much better gift than the hydrogen balloon.
Hey Corona, I noticed that it started raining outside. You should go home before it starts raining too hard.
I did notice some clouds. You're right. I better leave before it starts raining.
Bye Corona. Enjoy your new earrings.
Bye, Corona.
Did you guys think that you should have told Corona that lithium explodes and catches on fire when it gets wet?
Well, he did say he wanted to learn chemistry.
And the earrings did look good on him.
You guys are bad.
Those guys are really good to me. These are some really nice earrings. Ouch! Damn.
And now you all know that lithium will explode and catch on fire when it comes in contact with water.
In our next lesson, we will go over the beryllium atom. See you later.
So long.
Bye.
Well, this is our new baby brother, Jacob.
I know where he came from, but how did they make him?
If you ask Mom, she will say it was the chemistry between her and Dad.
Isn't chemistry wonderful?
Okay. Okay. Are you there? Can you hear me? Okay, let's go to another one. Let's see. Einstein.
The periodic table and atoms that make the Kids for Chemistry program so
Justin, can you count?
yes.
Well, let me hear you.
One.
Well, go on.
That's all I need to understand hydrogen.
But I want to hear you count to 20.
Hey, I'm a chemist, not a mathematician.
Wow, I like that answer. I think I'll try that line on Awa, can you count to 20?
What? Of course I can. You think I'm stupid? Let's hear you count to 20.
Okay. Hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine.
What are you doing?
I'm counting the first 20 atoms.
What happened to 1, 2, 3, 4, 5, 6, 7, and up to 20?
Well, Awa, we're chemists, not mathematicians.
I can't believe he stole my line.
The point that Justin is making is that hydrogen is made out of one proton and one electron. That is why it is the first atom on the periodic table. And if you can count to 1, then you can understand hydrogen.
And if you can count to 20, then you could understand the first 20 atoms of the periodic table.
And in the last lesson, we explained that atoms are made out of protons, neutrons, and electrons, and explained that the structure of the hydrogen atom with the help of orbital. Orbital, can you help us with the hydrogen atom again?
Of course. The hydrogen atom has one proton and one electron.
And remember that hydrogen does not have a neutron.
Today, we are going to go over the helium atom. Orbital, can you show us the helium atom?
Sure. This is the structure of the helium atom. It has 2 protons, 2 neutrons, and 2 electrons.
Helium is number 2 on the periodic table. And notice that it has 2 of each.
What is interesting is that hydrogen is number 1 on the periodic table, and it has 1 proton and 1 electron. And helium is number 2 on the periodic table, and it has 2 protons and 2 electrons. So the number of electrons and protons will match the number on the periodic table. This is the trend for all atoms on the periodic table.
But helium also has 2 neutrons.
But the number of neutrons does not always match the number of the periodic table.
The protons and neutrons are in the center of the atom and is called the nucleus. And notice that the 2 electrons are in the same orbital. The maximum number of electrons that can be in an orbital is 2.
And what will happen if you have 3 electrons?
Then a new orbital will be formed. We will discuss this later.
Okay. And remember, that the orbital can be thought of as a cloud, and the two electrons can be anywhere inside the cloud.
Oh, by the way, Orbital, we have a present for you. It's a balloon.
No, I'm not going to fall for that. After what you guys did to the coronavirus, I don't want any balloons.
Don't worry, Orbital. We like you. We're not trying to get rid of you. This balloon is a helium balloon, not a hydrogen balloon. Hydrogen is explosive, but helium is inert, which means it will not explode or react with anything.
You are absolutely right. Helium is okay. Helium is a gas and helium is inert. So, okay, I would love to have a helium balloon.
Hey guys, I would like to have a helium balloon also.
Oh, wow. Is he still around?
Hey, Corona, we don't have any more balloons for you, but we have something even better. We have some lithium earrings for you. We will give them to you in our next lesson when we go over the lithium atom.
Okay guys, I'll see you in the next lesson.
And we will discuss the third atom on the periodic table, which is lithium.
And here is something for you to think about. If lithium is the third atom on the periodic table, how many protons and electrons does it have?
So until then, see you later.
Okay, I'll see you tomorrow.
Remember, Justin, college begins in kindergarten.
All right. And if I have time, I will play another one. Hold on.
The periodic table and atoms that make the kid for.
Okay.
Hello, the kids for chemistry are here again. I'm Gerald.
And I'm Ava. And today we are going to go over the special drawings of the periodic table and atoms that make the Kid for Chemistry program so great and unique. These drawings have never been used before.
That's right. They are original drawings developed by Kids for Chemistry, and they are what make it easy for young children to identify the atoms and understand their structures.
Let's start with the drawing of the periodic table. Notice the side bar and the bottom bar.
What the? Where did you come from? And who are you?
Wait a minute. I recognize you. You are Albert Einstein.
That's right. I am the ghost of Albert Einstein.
What do you want? Why are you here?
Well, there have been stories going around the ghost vine.
The ghost vine? What's the ghost vine?
It's kind of like the grapevine, only the ghost vine is for ghosts. So I heard it through the ghost vine that the kids for chemistry had a new way of teaching chemistry. And it's designed so that younger children can understand. So I came to see for myself.
That's right. We have developed patented drawings of the periodic table and the first 20 atoms.
But there are over 100 atoms on the periodic table. Why are you only going over the first 20?
Because our patented drawings are based on S and P orbitals. When you go past the first 20 atoms, then you start seeing d orbitals and f orbitals, which are very hard to describe and very difficult for young children to understand.
But the S and P orbitals are simple enough that young children can understand.
Well, how young are you talking? Because they say that chemistry should not be taught until high school.
We have a new way of teaching chemistry. We believe that children as young as 4th and 5th grade can understand and learn.
So you're thinking outside the box. I like that. But how did you come up with these new drawings?
We just use our imagination.
Well, you know what I always say?
No. What do you always say?
Imagination is more important than knowledge.
Wow, I like that.
But I have a question for you. What are young children going to do with these chemistry concepts?
Well, hopefully the same thing that you did with these concepts. Help us to understand the universe.
Let us show you how these new patented drawings work.
Okay, I can't wait to see this. This is so exciting.
Let's start with the periodic table. Notice the sidebar and the bottom bar.
The sidebar shows how many s orbitals an atom has for each row and makes it easy to determine which row an atom belongs in.
What do young children know what an s orbital is?
That's why we're here, to teach them. An s orbital is round and spherical, and it looks like this. It's very easy to visualize.
Keep in mind that we will discuss S and P orbitals in more detail in our lessons. But for right now, we just want to give you, the great Einstein and all the teachers in the world, a feeling for how we use our patented drawings.
Some atoms will have more than one s orbital. If we look at the periodic table, all the atoms in the first row have one s orbital. All of the atoms in the second row have two s orbitals. All of the atoms in the third row have three s orbitals. And all of the atoms in the fourth row have four s orbitals.
I never saw the periodic table drawn this way.
The s orbitals look like concentric circles. So there is one circle inside another circle. And so you will have an outermost orbital, and when looking at atoms, we will always want to know what the outermost orbital is.
Can you give me an example of the outermost s orbital for an atom?
Sure. If you look at this atom, you will see that the s orbital extends further than anything else, which makes it the outermost orbital.
Oh, I see.
Now the bottom bar shows the electrons in the outermost orbital. S orbitals are the outermost orbitals for columns 1 and 2. The atoms in the first column all have one electron in the outermost s orbital. And the second column has 2 electrons in the outermost s orbital.
P orbitals are the outermost orbital for column 3 to 8. Column 3 has 1 electron in the outermost p orbitals. Column 4 has 2 electrons in the outermost p orbitals, and so on.
Wait a minute. Do young children know what a p orbital is?
That's why we're here, to teach them. A p orbital looks like the number 8, and it looks like this.
Yes! Yes! You are absolutely right.
The p orbitals are in groups of 3 and will look like this. If you have 1 electron in the p orbitals, it will be in column 3. If you have 2 electrons in the p orbitals, it will be in column 4. And if you have 3 electrons, it will be in column 5, and so on. So columns 3 to 8 have outermost p orbitals.
Can you give me an example of an outermost p orbital in an atom?
Sure. If you look at this atom, you will see that the p orbital extends further than anything else, which makes it the outermost orbital.
Einstein, can you tell me what row this atom is in?
Well, it has 2 s orbitals, the red circles. Therefore, it must be in the second row.
Can you tell us what column it is in?
The outermost orbital is the p orbital, and it has 4 electrons in the outermost p orbitals. Therefore, it must be in the 6th column, and the atom must be oxygen.
That's right.
That is incredible. It is so easy to identify an atom. And you can see how many s orbitals there are and how many p orbitals there are. And you can see what the outermost orbital is. This is so simple.
Well, the good thing is, you don't have to be an Einstein to understand how to use our drawings.
Brilliant! Brilliant! This is so important for schools going through a major reform in their science curriculum. Kids for Chemistry is the ultimate goal for a STEM education. You guys were really thinking outside the box and used your imagination.
Well, like you said, Einstein, imagination is more important than knowledge.
You know what? I really like your channel, and I'm going to subscribe to it.
Great. And if you also like our channel, please hit the subscribe button below.
So,
See you later.
Thank you so much. Those videos were so cool, and I learned a lot. And seeing the SP orbitals reminded me of my chemistry class, and I didn't learn that to college. So it's great to see kids to learn that a lot earlier.
Wow. Okay, sorry about Okay. All right, just to let everybody know, you can visit these videos. We're producing these videos as you speak, and we got a whole series of videos that are just like this and just going through the first 20 atoms. But you can visit these if you go to YouTube and you put in Kids for Chemistry. Now that's not chemistry for kids. Do not put in chemistry for kids, but put Kids for Chemistry and put quotes around it, double quotes around it. It'll take you right to these videos and you can see. So if you can, visit the videos, subscribe. And we just started producing these about a couple of months ago. So we got many, many more in mind. So thank you very much for having us.
You're welcome. That was so great. And thank you so much. So we'll put the videos in the chat. And thank you so much for making time of your day to be a part of our chemistry week.
No problem. Thank you for having me.
You're welcome. So what we are going to do now, we're just going to take a quick break to play. We're going to start our Jeopardy game, which we're going to finish after our next two speakers. But I want to give you one quick break just to kind of warm up with your chemistry Jeopardy. So I am going to share my screen. And we are just going to play one row just to warm you up. And then we're going to get to our next two speakers. Okay, so we are going to shop. So we are just going to do this row for, I am thinking that we are going to do, history of chemistry, parts of an atom, atomic mass, and what is matter. So I think we are going to start with the row of what is matter, because matter is just a basic form of what everything is made up of. So let's do the first question 400. What is matter for 100? Anyone have a guess? What is matter? The first thing is anything. This is anything that takes up mass in space. So I'm going to find the answer. Matter. What? Okay. Let me try another question. The smallest pieces of matter are called. You can put your answers in the comment. What are the smallest pieces of matter? Okay. Atoms. So atoms are the smallest pieces of matter. What is matter for 300? What type of particles hold the protons and neutrons together in the nucleus of an atom? So remember, this is just getting you wet. So we're going to really play hard Jeopardy after our next two speakers. Masons. I didn't even know that, so I'm learning something. What is matter for 400? Up, down, strange, charm, top, and bottom are all the names for what type of particle? Okay. Quarks. And the final Jeopardy question. What type of particles are quarks held together by? Gluons. Okay. So I was just doing that to warm you up. And we are going to go to our next speaker. So remember, after these two speakers, you have to be prepared to play Jeopardy. So we are going to our next speaker, Ms. Aria Lane of STEM Assist. I'm going to add to the stream.
Hello, hello.
Do you have a screen to share, or you're just going to do your...
I'm just going to talk off of the board I made and then the demonstration.
Okay, well, I'm going to head out and let them enjoy your chemistry demonstration. It looks so fun.
All right.
Oh, sure. Okay, I'm sorry. I took you out instead of myself. Let me take myself out. Moving too quickly.
All right. Hello, everybody. I'm Aria Lane from STEM Assist. STEM Assist is an organization whose mission is to help prepare the high school student to transition into majoring in STEM in college. Okay, so we provide different resources, curriculum, study tips, and strategies to help with that. All right, so today we are going to be celebrating, of course, National Chemistry Week. But specifically, we're going to be making bath bombs. All right. I'm not sure if you all are familiar with bath bombs, but it's a great thing to not only make, but to definitely use in your self-care practice, which everyone should be doing now during these times. Okay. So before we get started in the actual demonstration, I want to talk about two important concepts dealing with bath bombs and how they incorporate into chemistry. The first concept is known as acid-base chemistry. So we'll be using an acid and a base today. And when acids and bases are put in water, they dissociate or dissolve and break down. And this reaction is known as a neutralization reaction. All right. So this neutralization reaction actually has reactants, like all reactions do, and products. So specifically for a bath bomb, today we'll be using the acid known as citric acid and the base known as sodium bicarbonate or baking soda. We're all familiar with baking soda. So if you're familiar with the bath bomb, you know that when you put it in the water, it breaks down into, most notably, gas. You see the fizzing from that particular bath bomb. All right, and this gas is a product, and this gas is specifically CO2. Now, there are also other products, water, and then salt or sodium citrate. Okay, so again, this is known as a neutralization reaction. When you put acids and bases together, you know, acids have a low pH, 1 through 6. 7 is neutral. Bases high, 8 through 14. When you put them together, they'll neutralize or probably be somewhere in between at that 7. Okay, now the second concept deals with the smells of the essential oils that we'll be using in the bath bombs. So a lot of bath bombs, when you fizz, most bath bombs, when you put them in, not only do you want the effect to be in your bathtub, the bubbles, but also the smell and the aroma. Well, that comes from the essential oils that are used in the bath bombs. Did you know essential oils are all about chemistry? Specifically, essential oils are oils that you can get from a plant, but they have different properties, and these properties are based on the constituents or the parts of the molecules. All right, so this is, I'm not sure if you can see this. Zoom in a little bit. All right, so this is an aldehyde, which is known as a functional group. All right, so this is an essential oil known as cinnamonol. Yes, it's from cinnamon, excuse me. All right. The basic or the most prominent functional group in cinnamon is aldehyde. All right. So these aldehydes are very infamous or known to be in a lot of citrus smells. So if you smell citruses, more than likely they'll have aldehydes in it. But mostly essential oils can be broken down into hydrocarbons or having hydrocarbons or oxygenated compounds like aldehydes. Another example of oxygenated compounds include esters. Esters give you like a sweet smell. So your lavender essential oils have esters in them. Example of hydrocarbons include your terpenes. So your pine oils that you might smell when cleaning something have hydrocarbons as well. Okay, so again, before we get started, two basic concepts. Neutralization reaction with the acid-base chemistry, and then we also have functional groups that deal with the smell of the essential oils. All right, so before we get started in actually making the bomb, I want to show you the acid and base we have. All right, so I'm just going to kind of scoot down to the table. Hope you can see that. All right. Okay, so we have here lemon salt or citric acid. I just got this from my local farmer's market. Again, this is our acid. So I made a solution of the acid, and the solutions are just where you place a solid into water, an aqueous solution, and we're going to test it using pH strips. All right. So acids, like I said, are going to be on the lower end of the scale. All right. So according to this particular color indicator, sorry if it's not clear. All right, it's going to be in the lighter colors. Okay, so I'm going to dip this in here. And as you can see, yes, it is pretty red. All right, so the red again is going to tell us that we have an acid. And if you can't see, again, the red is 1 through pretty much 1 or 2. So very acidic. All right, we did the same thing, or I did the same thing with the baking soda. All right, so again, this is our base. So I made a solution of baking soda, and the bases are going to be a higher pH. So on this color indicator, it should be blues, greens, very dark. All right, so I'm dipping my pH strip in, and yes, it is blue. All right, so we do have acids and bases, which means, again, what type of reaction? Neutralization reaction. Okay, so these are the basic ingredients you need to make a bath bomb. Right, so you're going to need a bowl so you can put everything in. Of course, let me move these out the way. All right, of course, you're going to need baking soda, like we said before, your citric acid. You're going to need some coconut oil. Olive oil is good as well. Epsom salt or sea salt, either or is fine. Epsom salt's chemical name is magnesium sulfate. And the cornstarch will help kind of put everything together. You'll need an essential oil. Any essential oil will do. You want to make sure that the essential oil is not for specifically aromatherapy, but actually can be put on your skin because you're going to be bathing with this bath bomb. You'll need a spray bottle of water and a measuring cup. So you'll need, in this case, I'm using 1/4 cup and 1/4 teaspoon. Depends on how many you want to make. I'm just going to make 2, but you can pretty much find these recipes anywhere online. You can find how to make them. Okay, so we're going to start off with our baking soda. And I'm going to use 1/4 cup. Right, I'm putting it inside. Okay. We're going to use 1/8 cup of citric acid. All right, I have 1/4 cup, so I'm just going to half that. I had a spoon. Oh, here we go. All right. Next up, we're going to use our cornstarch. All right, so our cornstarch, we're going to add 1/8 cup of cornstarch. So same idea, half of the 1/4 cup. All right. Put that aside. All right, and the last solid, so you want to add all your solids first and then add your liquids. We're going to add is the Epsom salt or the magnesium sulfate. And we're going to add 1/8 cup of the Epsom salt. Just make sure all of that is out. All right, so I'm going to fill my 1/4 cup up halfway. There we go. Okay, so again, it was 1/4 cup of baking soda, 1/8 of a cup of citric acid, 1/8 of a cup of cornstarch, and 1/8 of a cup of the Epsom salt. Okay, we're going to go ahead and stir that around. Now you can make these also with color. I made a few earlier in the week, little Halloweenish with the black and the orange. And you can use dye, food coloring, or they also have soap dyes that you can use. Or I like to keep it very natural. I love herbs, so you can use, actually for the orange, I use turmeric. Turmeric, it has lots of great properties for inflammation, so that would help in the bath bomb with the soothing and the relaxation. The black, actually, I used charcoal. All right, so charcoal is also really good, has lots of health properties that you can use. So in that case, if you use powder or herbs, you would want to add it with the solids. All right, you're going to stir it around and make sure there's no clumps. I'm actually going to switch this. All right. Okay, so now we're going to add our oil. So again, you can use olive oil or coconut oil. I'm going to use coconut oil. And this is 1/8 a teaspoon. All right. And the last thing is just 1 to 2 drops of essential oils. All right. I have this essential oil. It's a mixture of oils, actually, very citrusy. I love grapefruit. Anything that will awaken me in the morning. I like to also put my bath bombs in the shower. 1, 2. It lasts longer because, of course, you're not directly hitting it with water, but it also gives you that same aromatherapy feel while you're taking your shower. So I love citrus smells, all right, or those aldehydes in the morning. All right, so we're going to stir this around. If we were in a lab, we'd be using goggles because it is a powdery substance. So be careful when you stir it around. All right, and when you stir it around, you just want to make sure there's no clumps. Okay. All right, so again, you can add powder if you like to color it. I'm going to add just a little color so you can see instead of the white. Be careful with the color you decide to use or the particular herb. Turmeric stains, charcoal stains as well, so just be careful. Okay, so now with the spray bottle has the water in it. And the reason we're using a spray bottle and not just pouring water in it, you need about, I think it was a 1/2 teaspoon of water. We just don't want to pour the water in it because, again, this is an acid base. When we add water to acids and base, they disassociate, they dissolve. So that fizzing is going to happen too soon. All right, so you want to just spray in certain areas to avoid it fizzing. And when you spray, you'll actually see the fizz. So just be very careful. All right, so we're going to just spray a little bit. You can actually hear and see it. And we're just going to kind of move it around with our hands. This is where it gets fun. You can move it around in your hands. And you're going to keep spraying until you get a consistency enough, kind of like sand, all right, where it stays together. So right now I didn't put enough because it's not staying together. I'm going to add a little bit more. Again, I'm careful with it because I don't want to wet the entire thing and ruin the reaction before I get to the bathtub. All right, a little bit more I think we'll do. All right, and in this case, you can use a mold. So I've seen ice cream scoopers be used. You can put in an ice cream scooper. You can mold it in a cupcake pan. I'm just going to mold it with my hands into a circular ball, but you can really use any mold that you have. All right. And you know, it's not going to be a perfect circle, but we get the point. Okay, so here's our bath bomb. All right, so you're going to, it's not ready yet. If you put it into the water now, it's going to just fall apart because it's wet. So you're going to actually put it on some parchment paper for 24 hours. All right, and then you should be able to use it after 24 hours. Okay, so that's it with the bath bombs. I want to go ahead and show you what one would look like. You can pick up bath bombs anywhere, so if you don't want to make one, even though it's lots and lots of fun and very easy to do, you can pick up bath bombs anywhere, and they have those ingredients we talked about. But I want to show you that reaction. So we'll open this up. All right, y'all. There we go. Okay. These have plastic in them. So yeah, usually you'll put, if you're making these, I know a lot of businesses make them, a lot of soap making companies. So they'll cover them. If they send them to you, they'll cover them in something to reduce the humidity or any effect that the water vapor in the air might have on the reaction. Remember the neutralization reaction. Okay, so we're just dropping this into here. And as you can see, I'm hoping there's some fizz coming. And depending on how many bath bombs you use, of course, it'll fizz throughout your bath. All right. Again, you can also use them in the shower. All right. So thanks for joining me again. I hope you have fun with this. And remember some basic concepts, acid-base reactions and neutralization, as well as functional groups and those good smells you smell and the bad smells. So like rotten eggs is a sulfhydryl bond or functional group. All right. So whether it's good or bad, it deals with functional groups. But lots of fun chemistry and self-care. Thanks again.
Aria, before you go, Before you go, I have a quick question. So you say sometimes you use them in the shower or the bath. That adds different moisture level to it. So how does the reaction go in the shower? Does it have the same type of fizz or it just lets the aroma?
Good question. It's mostly the aroma because, again, if you want the full fizz effect, you should put the entire bomb into the water. But because I know I placed mine in the corner, so the shower faucet is towards me, I'll put mine behind the shower faucet because I don't want the water. I don't want the fizzing effect. Like you said, I just want the aromatherapy effect. So the water vapor from the shower, that steam, will eventually dissolve and those particular essential oils and the smells will come out.
Okay, and then one last thing. Can you explain functional group? Because I have memories of organic chemistry when you said functional group and I saw your...
Yes, so functional groups are just like parts of molecules. And there could be more than one functional group on a molecule, but they really give a characteristic or a quality to that particular molecule. And the quality can be some type of nerve enhancement, so feeling euphoric or relaxing. Most notably for the bath bombs, the aromatherapy aspect or the smell aspect can come from the functional group. So the aldehydes I mentioned are a functional group, specifically an oxygenated functional group, and they're very popular in the citrus essential oils. So like the lemons, the grapefruits, if the citronella candles that we burn, like to keep the mosquitoes away, that all has plant essential oils that, and those essential or those particular plants or essential oils have that aldehyde functional group. So functional groups just give a particular molecule some flavor a little bit.
Thank you so much. You explained it a lot easier than my organic teacher. I think you've gotten it.
Right.
Well, thank you so much to know that chemistry, we say chemistry is everywhere, right? But how integral chemistry is in our self-care and skincare, right? All of our products.
Definitely.
So thank you so much for making time to show us how to make a bath bomb. And you said that they can find that experiment like online. It's a lot of different ones they can use.
So if you just Google bath bomb recipe, you can choose the one to your liking. The basic ingredients are the ones I use. So baking soda, Epsom salt, the citric acid, which you can find in your grocery store, coconut oil or olive oil, your cornstarch, and the essential oil. So you can Google for like specific measurements, but as long as you have those ingredients, you'll be good to go.
Okay, and one last question before we go on to our next speaker. Why is measurements important in this? Can you mess up your bath bomb if you don't follow the measurements?
Definitely. So we didn't get into limiting reactants or anything like that, but there's certain ratios that are important between that acid and base, or between that citric acid and the baking soda. So you put too much acid, you might not get the fizz like you want, or not enough carbon dioxide, because that's the source of the CO2. You wouldn't get that same reaction when you put it into the water. So it's so important, and you can play around with it if you want. Once you start making your bombs, you can see yourself, oh, if I put more carbon dioxide and less acid, will it fizz more? It's a great little science experiment, right? Or if I put less, will it fizz even less? All right, so measurements are so important if you want to get the right output or product.
Well, thank you so much. That was so fun. I'm not going to make a bath bomb. I'm going to buy them. But it's good to know that it's a simple chemistry experiment. And just a reminder, when we talk about chemistry is really everywhere, it is, right? How we take care of our skin. So thank you so much. And thank you so much for being a part of our Chemistry Week celebration.
Thanks for having me.
You're welcome. Bye-bye.
Bye.
Okay. So that was so cool. So we are going to get ready to have our final speaker before we do another round of Jeopardy, Mr. Robert Grover of Databot. And he is going to do some really cool chemistry experiments. So I'm going to let him into our broadcast and just have him introduce himself and get right to his experiment. Hi, Robert. How are you?
Hi, I'm great. Happy Saturday. It's good to be here.
Thank you so much. So I'm so excited, and I know you're going to close our chemistry week with a bang. So I'm so excited. So just tell us a little bit who you are before we start our experiment, and then I am going to log out and just let you do your chemistry demonstration for us.
Great. Well, I've been involved in STEM education for over 30 years, and I've taught everything from chemistry to robotics and coding and engineering, and had a lot of fun doing that. And everything I've always done has been around hands-on experiences. So kids are always creating, producing, designing something. So it's been a lot of fun. In the last few years, I started a new company, and it was based on a lot of the things I'd done over the last 30 years. And we created this new product, which we're going to use actually today in these experiments, called Databot. And Databot fits in the palm of your hand, and it's got a dozen sensors that you can use within it. And those sensors allow you to explore all the invisible forces that are around us, whether they're gases that you can't see or acceleration due to gravity, all kinds of fun things. So the sensors that are built into it allow you to read light, ultraviolet light, sound, humidity, atmospheric pressure. One of the things we're going to look at today is the density of gases. We'll talk a little bit about atmospheric pressure. But the experiments that I typically do all get to display data using Databot, and I'll show you how that's done today. And it's really interesting because we don't realize, we talk about it in theory and we try to imagine what these forces are that are around us. But Databot and using sensors allows you to actually visualize things that are typically would be invisible for us. So that's what we're going to take a look at today.
And you know what? That is pretty cool. When you think about, I'm so glad you are here, because typically when we think about science and scientists, sometimes we forget how interdisciplinary it is, right? And you are using chemistry, computer science, electrical engineering with the sensors, right? Mm-hmm. And how different STEM professionals in STEM disciplines can work together for us to find answers to the problems and questions we want to answer. So that is so cool. So chemistry can stand alone, but chemistry can work with other STEM disciplines. I mean, have I missed it? Physics, robotics, computer science, electrical engineering, right? All of that works together to create your data bots to collect data for, right?
Exactly. Yep. And truly interdisciplinary, because the the set of sensors we put on this allow you to actually do explorations in earth science, chemistry, physics, environmental science, even life science. So we have one activity where students actually build a model of the human chest cavity, and Databot travels inside the human chest cavity and looks at the change in pressure inside your chest as your diaphragm moves. So all these things are interlaced and interrelated. So that's one of the best things about science, I think, is it's just this amazing puzzle where everything's tied together.
That is cool. Well, I am going to get out and let you show us how the Databot works and shows the interdisciplinary of chemistry and how it's connected to so many other STEM disciplines.
Great. All right, so today, the activity we're going to do is called the Cave of Dogs. And I call it a science mystery because there's something interesting that goes on in this cave, and it's a real cave. I'm going to show you a picture of it here in a minute. And something happens inside the cave that is truly mysterious, and it's going on because of something, again, invisible that we can't see. And it has to do with chemistry, it has to do with gases. So let me, I'm going to see if I can share my screen here, and I'll actually show you a picture of the Cave of Dogs. And I'm going to ask some questions as we go through this. Let's see here. And there we go. I'm going to share a Chrome tab. And there we go. Now, hopefully everybody can see this. Let me see if I can zoom in on it here. We'll go full screen. Now, this is a picture of the actual entrance to the Cave of Dogs. And as I said, it's a real place. It's located in Italy, and it's in a active volcanic area. So there's something going on with gases that has to do with volcanoes, okay? And the mystery of the cave is that people can go into this cave, and if they're taking their dog, you can see my little picture down here in the corner. Let's say that you walk into this cave, you and your friend and your dog go into the cave, and you can look around, you can explore, and everything's fine. You know, you're looking at the cave and checking things out, but your dog might pass out. And that's why they call it the Cave of Dogs. And it's all about gas. So my first question, and all of you can put your answers into the chat stream there, is why do you think the dog passes out, but the people don't? Because we all breathe air. We're pretty much, we're very similar physically, and we're all breathing, you know, we're different sizes and things like that. But why would the dog pass out and the people not? And as we go through these experiments, each one of these experiments is going to give you a clue. And by the time you see the end experiment, you'll understand why the dog passes out and the people don't. But see if you can figure it out as we go along. So we're going to do 4 quick experiments. I usually do this over 45 minutes, but we're going to go through them a little faster today. First of all, we're going to do a chemical reaction, and very similar to the last one you just saw, it's a base acid reaction where we're going to actually create and capture CO2. And all of these experiments are on our website actually with videos, so you can actually do them at home after you watch this, and they're quite fun. The second experiment is called the weight of air, and we talk about, does air have weight? Do gases have weight, or are they just floating around out there and they're weightless? The next one is actual demonstration of carbon dioxide versus air. We try to figure out which one might be heavier if they do indeed have weight. And then finally, we actually build and demonstrate what's going on in the Cave of Dogs using a simulation. And again, all the instructions are online. You can build your own Cave of Dogs and do this demonstration at home when we're done. All right, so what I'm going to do here is escape out of that. And we're going to do our very first experiment. And to do that, I have to stop sharing so that you can see my video stream. And there we go. You should be able to see me again. So the Cave of Dogs. So the first thing we're going to do, we're going to create a chemical reaction between a base and an acid, and we're going to generate carbon dioxide by mixing them together in this bottle. So just a regular 2-liter pop bottle. You probably have something like that at home. The acid we're going to use is vinegar, probably have some of that at home. And we're going to use baking soda, which you guys probably have both of these things at home. So it's very easy to do. And they're not dangerous at all, but it is fun. Okay, so the way I do this, I'm going to tip my screen a little bit so that you can see how we're mixing it up. Set that off to the side. Here's my vinegar. Now, when I do experiments, I always want to be super tidy. So I use things like funnels. It's a little funnel that fits in there. It keeps me from spilling things. I like to use precise measurements. You know, we talked about that in the previous activity. So I've got this measured into a beaker. And you can use measuring cups at home. But try to be super tidy and organized. I always have my materials set up and organized so that it's not going to make a mess. We're not going to break anything. And I'll take that off and I'll set that to the side. So now we have our acid, right? And now what we're going to do is take our base. And this is the fun part. A lot of people haven't seen this. Some people may have done it. But I take my baking soda, which I've got here in this little beaker again. And I'm going to take a balloon like so. I'm going to stretch it over my funnel like so. And then I'm going to pour the baking soda into the balloon this way. And in a few minutes, you'll see why we're doing this. Again, being super tidy, I've got a nice funnel there, so I capture everything. Sometimes things don't always work out. I actually had the balloon explode on me once when I was doing this experiment, and it was very spectacular. We had baking soda and vinegar everywhere. So now I'm taking that off like so, and I've got my balloon full of baking soda. And this is the fun part. This is how we actually capture the CO2 for the experiment, okay? So what I do is I stretch the head, or over the head of the bottle, the balloon, like so. And now I can actually shake that baking soda, my base, into the vinegar, my acid, and it'll react down there. You should see it fizzing, and then you can see immediately that one of the products, you know, we have reactants and we have products. The product that we're capturing here is actually carbon dioxide, or CO2. And we're actually going to use this in an experiment, is why I'm capturing it. And there we go. Get it all in there, and boom. I've actually got a little hole in my balloon. There we go. There we go. Okay, I'm going to set that aside. I'm usually a little tidier than that. I made a little bit of a mess, but we did capture our CO2. Now, to do these experiments, I use very simple materials. So we've got it in a balloon, and I'm going to use what's called a binder clip, if you can see that. Okay, binder clips are used to hold papers together, but in this case, I'm going to use it to hold my balloon together, like so, because I don't want my CO2 to escape. So there we go. And that makes it easy to take it off later, so I don't tie the balloon off. I use actually a little binder clip to hold it. And some of these other experiments, which you'll see in a minute, we use binder clips quite a bit. Okay, so that's part one. And the hint with that is carbon dioxide is actually what's happening in the cave. There's something to do with CO2 that's hurting the dog, putting the dog out, you know, to sleep, and it's not damaging the people for some reason. So again, there's your question. What's going on with the carbon dioxide? Okay, I'm going to share my screen again, and we're going to go on to the next part here. Okay, next experiment. Okay, we've talked already about chemical reactions, which is what we just saw. We're going to skip over that, and we're going to go on to the next question. And this one is, does air have weight? Now, I think in the previous activities, you've heard the terms mass. So we've talked a little bit about what is mass. Volume is the amount of space something takes up, okay? So like in our balloon, if we were to measure that balloon somehow, that would be the volume of the CO2 we have. Density is how much matter there is in a particular volume, okay? And then weight is actually a relative term. It's based on gravity. And if you have the same amount of mass, for example, on Earth or on the moon, its weight may be different because gravity is pulling on it differently. So anyway, these terms all have to do with what's going on in the cave, okay? Density is the most important one. So what we're going to do is take a quick look at another experiment, which I actually have a video of that Normally I show you how to put this together, but since we're down to just 15 minutes, we're going to do it just going to the video. So I'm going to switch over here, and these actually are the instructions that are online. And let's see, we just did that one. This is the one we're going to do next, where we actually determine if air has weight. And if you haven't already, put your comments into the chat about whether you think air has weight or if it's weightless, okay? And here's the experiment. And again, you can do this at home. So the materials you need to create a scale look like this. You need a yardstick, binder clip. You can use a pencil or a dowel. And what you do with those is you make a big scale. And it's a very sensitive scale using just very simple materials. So you can see how I've done this at home. I use binder clips, and I use a paper clip. And then you can see the paper clip on this picture is actually hanging onto that balloon. Okay, so that balloon's full of air. And there's actually a video here that we're going to watch where we compare to see if air has weight. So if you haven't made your guess yet, please do so. And what we're going to do is take a look at a video that actually demonstrates whether air has weight or not. So there's our scale. And you can see it's just kind of balanced there. And we're adding one balloon full of air. And again, you can do this at home. It's a little tricky because you have to make sure that the balloons get the exact amount of air in them so that they're balanced, right? So right there, there's our scale. And now we know that we've got balanced balloons full of air. And you can use things like a cloth tape to measure the circumference of your balloon to get it close. When I did this, I had to let a little air out of one until it finally matched the other one. And then I got a perfect amount there. Now, the way we weigh air is we're going to take one balloon. We're going to remove all the air from it, which you can see me doing there in this video. And then we're going to hang the empty balloon back on the scale. And everything's exactly the same except one balloon has air and one doesn't. So let's see if it has weight or not. And there you can see, indeed, air does have weight because this side's heavier. It looks like maybe not a lot. I bet it doesn't weigh very much. And actually on the website, the information on how much air does weigh is presented there. And you can actually calculate the weight of air in your house or in your living room, which is kind of fun. So that's part one. Now we've just demonstrated that air has weight. Now, if we were to compare a balloon full of CO2, like the one that we just created, to air, do you suppose CO2 is heavier or lighter than air? So that's what we're going to weigh now. We're going to weigh air. We're going to put a balloon full of air on one side. You can see my fancy handwriting there. I've labeled it. That's the air one. And then we're going to put a CO2 balloon on the other side. Now, if you haven't put your guess in, go ahead and put it into the chat stream again. Let me know if you think air is heavier or lighter than CO2, or maybe they're just the same. Maybe all gases weigh exactly the same. And here we go. Oh, you can see that CO2 balloon is actually quite smaller as well. Now look at that. We have demonstrated right there with some very simple apparatus that CO2 is actually much heavier than air. Remember how just taking the air out of the balloon made very little difference, but you could see it was heavier. When we do the CO2 is obviously a lot heavier. So that's our next clue. Okay, so let me go ahead and escape. Go back over here real quick. So we've just demonstrated that. And we just demonstrated that CO2 is heavier than air. And now what we're going to do is take a look at Databot. I'm going to give you an example of how we actually capture CO2 data. And then we're going to take a look at our Cave of Dogs simulation, and we'll actually demonstrate what's going on in the cave. So again, with the information you guys have received, if you've figured out what's going on with the dog in the cave, go ahead and put that into the chat stream. Because the more you see what's going on, you know, we're learning about CO2, we're learning about density of gases. I'll give you another clue. What's going on in the cave? You know, I mentioned volcanic activity. There's what's called a fumarole in the cave, and it's seeping gas into the volcanic or into the cave opening. So you've got this steady stream of CO2 coming in. So now I'm going to unshare my screen. I'm going to show you how we connected Databot and actually look at data. Okay, so I'm going to use just my tablet here. And I use an application. It's a smart device application called Vocs, which let me get it up here on the screen. This is also something you can find on our website. Now, Vocs is a free application that you can download to your smartphone or your tablet. Works on both Apple and Android platforms. And it's a free app that actually uses the sensors in your device. So just like Databot has a bunch of sensors built into it, your smartphone does. You can actually do experiments just using this free app. So you can measure motion, you can measure light, sound, all kinds of fun things. So Vocs is a lot of fun. I recommend you going out, downloading it, testing it. Now to connect to Databot, Databot connects wirelessly. You can see a little blue light flashing there. That's its Bluetooth signal. And what I'm going to do is tap on Vocs and we're going to connect to it. It's really super simple to use. And right there, if you can see, okay, so we've got some data that's starting to read there. And it's reading the CO2 level on my Databot. Okay, so I'm actually going to breathe on Databot and we'll see if that goes up. It should, because when I exhale carbon dioxide, right? We inhale oxygen. We have all kinds of cool processes going on in our body that converts it to CO2, and then we exhale it. And you can see right there, it spikes up immediately just from my breath. So what we're going to do is now demonstrate the cave of dogs. We're actually going to simulate our own cave, and we're going to send Databot inside the cave so that you can actually see the change in CO2 levels, as well as a particular physical phenomenon that's going to take place as we pour the CO2 in. So to do this, I'm going to turn this around. We're going to stay connected to Databot. I'm going to adjust my screen a little bit here for you. And there you go. You should be able to see CO2 levels in the room. Again, I'll blow on it a little bit. And now this is my simulated cave of dogs. I love this experiment because it's got fire, it's got gas, it's got all kinds of fun stuff. Again, you can do this at home, and you can do it with a container like this or a more shallow container. I've done it with lots of different devices, and it's pretty simple to do, really. But what we're going to do is we're going to light the candles in here. And I think you probably all know that candles, fire needs oxygen, right? So in order for the candles to keep burning, they have to have oxygen. Just like we need oxygen to breathe and survive, candles need oxygen as well. So I'm going to light this one first. And you'll notice I've used Lego bricks to stack my candles at different levels. And this is part of the clue, actually, because as we pour the CO2 in, I want you to make a prediction. So again, is CO2 just floating around in there? And it'll put the candles out one at a time? Will it put the candles out at all? Will it put them all out, or will it put them out at different levels? Maybe the top one goes out first. Predict what you think is going to happen. So we're going to pour the CO2 in there, and we've demonstrated that CO2 is heavier than air, right? So that's a significant clue that I want you to be thinking about. And you'll notice also I've got my silhouettes here of my people. So I've got my people that are standing up here. I've got my little dog who's clear down here in the lower level. And what we're going to do now is I'm going to wrap this around this straw. And this is my simulated fumarole, right? So this is my, oh, I forgot to put Databot in there. You got to be able to watch the data. So we'll set him inside there as well. Now, another interesting thing, you might see the CO2 levels going up. I'm going to clear this and refresh it so we can see the data from the beginning. And there we go. There we go. It's waking up. So you can see our CO2 level in there. And it's reading out at the bottom here in parts per million. So 600 parts per million right now. In our room here, it's usually between 400 and 500. If you're in a room that's really crowded with people, you might have as much as 1,000 parts per million. And the more CO2 you have, different kinds of effects start to happen. So now what I'm going to do here is I'm going to start pouring the CO2 in from the balloon. And I want you to watch those candles carefully. Let's see. Now the first one just went out. You'll notice it's the one at the lowest point. I'm going to keep pouring in CO2. And you'll also notice what's happening on our graph there. Oh, the second candle just went out. It's a little bit higher than the first one. So they're going out from the bottom up. And why do you think that's happening? Oh, the top one just went out. And our CO2 levels are continuing to climb. I mean, it's just soaring there as I pour this stuff in. Just go ahead and finish it. Let's see what our top level was. So we maxed out over 60,000 parts per million, which is a very high level. And this particular sensor will only read that high, so it may have even gone higher than that. So we had pure CO2 in there. If I take this out, shake it around in the room, you can see the graph plummeting again. So now we know that this cave of dogs that we created was just packed with CO2, right? And interestingly, the CO2 filled from the bottom up, right? And that's because, of course, which we already demonstrated, CO2 is heavier than air. So now, last time I'm going to ask you, put it into the chat, why do you think the dog passes out and the people don't? And I'm going to share my screen one last time and show you a picture. Go ahead and put your thoughts into the chat and let's see if you figured it out. All right, now this particular screen shows you the effects that CO2 has at different levels, right? So I told you at 400 parts per million, that's pretty normal. As the concentration goes up, you start to feel more and more sick, right? Because it's not poisonous itself. What it's doing is it's displacing the oxygen. So as the CO2 fills the container up, it pushes the oxygen up. And in this case, as the level gets higher and higher and higher, there's no oxygen for you to breathe, right? And we need oxygen. So you can see that things like headaches, poor concentration, you start to feel sick to your stomach, all those things happen because suddenly your brain is not getting enough oxygen. And in the cave, if you haven't figured it out, that's exactly what's going on. So the cave has enough ventilation in it that the area is above about 1 meter in height. There's enough ventilation that it circulates fresh air in there. So the people are fine. They're walking around feeling good. But the dog is down there at a level below 1 meter. And look how high the levels are. So the dog doesn't have enough oxygen. So the actual mystery is that it's actually not just dogs, it's people too. If I was to bend over to tie my shoe and got down into that lower level, I'd pass out too because there's just not enough oxygen. So that is the end of the Cave of Dogs science mystery. And again, you guys can do all of these experiments at home. They're really super simple to do. I'm going to unshare my screen and come back. And if you have any questions, I'd be happy to answer them now.
Thank you, Robert. That was so cool. Like, you never really think, one, how gases impact different things, right? And then how, like, a toddler that may be the same height as a dog may pass out too, right? I mean, you shouldn't be walking with your toddler in a cave, but just if you are,
exactly.
it could pass out. So that was just so amazing and interesting to just see how chemistry, you know, is, we learn about the acids and bases, but also how we can use chemistry to answer questions that we don't know the answer to, right?
Exactly, yeah. And density of gases is very important. You know, there have been events all over the world that have to do with carbon dioxide being more dense than air. So, for example, you know, caves fill up with it. All kinds of businesses have to monitor for CO2. So, yeah, it's an intersection of, again, technology and chemistry. So, using things like sensors, we can identify where things might be dangerous. There's actually workplace requirements. The legal level is 5,000 parts per million. So, if you work in a mine or a location where there might be CO2 presence, you have to be monitoring for that legally as a company to make sure that your workers are safe.
And do sensors help keep us safe? Because you can send the sensor in, or, you know, the robot with a sensor in to test the levels of gases versus sending a person out, right?
Exactly. Yep. We have an activity that we actually do with kids that is a lot of fun. We use a robot like this, And we send the robot in under remote control, and it's got a Databot on there, and it's we call it a sniffer. It's looking for volatile organic compounds is the challenge. So being able to go in and look for things like dangerous fumes and not endangering yourself, you know, that's really an important thing. That's why things like sensors are so important.
Well, thank you so much, Robert, for showing us how the integration, you know, of chemistry tech can not only have us collect data, solve mystery, but save our lives, right? Because we want to breathe quality of air, good quality of air. We want to make sure our workplace and home safe, because you can use these type of sensors at home to monitor your carbon dioxide and any other gases.
Exactly.
I think carbon dioxide is the one at home that kills people, right? Like they wake up with carbon dioxide poison.
Yeah, carbon monoxide and CO2.
Monoxide, I'm sorry. Yeah, okay.
Yep, they're both dangerous. Carbon monoxide is the one that is the unseen killer, but like CO2 is a product of fire and smoke. So, you know, all those things are dangerous. And volatile organic compounds, that's another thing that Databot is capable of detecting. Those are very prevalent in houses. They are materials that evaporate at room temperature. And so VOCs, sometimes if you have prolonged exposure to VOCs and you can't see them, it can be very dangerous. And VOCs can be emitted just from the paint on your furniture. If you leave chemicals open under your kitchen sink, they'll be, you know, evaporating and putting VOCs into the air. So that's another experiment. We did a really fun project with Girl Scouts this summer, and a bunch of Girl Scouts had Databots, and they searched their house looking for volatile organic compound sources and making sure that their air quality is safe.
So Robert, before you go, someone has a question. Thank you for your question, Nathaniel. Is carbon monoxide heavier than carbon dioxide?
That's a really good question. You know, I don't know the answer to that, but we know that we might be able to guess, and then we could actually do an experiment like we just did. Now, carbon monoxide, the symbol for it is just CO, right? One oxygen, one carbon. So CO is carbon monoxide. Mono means one. Carbon dioxide is two oxygen and one carbon, excuse me. So CO2. So we could probably guess that CO2 is heavier than carbon monoxide because you've got two carbon or two oxygen atoms versus one oxygen atom. So I would guess that CO2 is probably heavier than CO, but you could always experiment to find out.
Experiment also look at the periodic table, right? Because it has the atomic masses of each atom, and then you can use those. Use the what's in the molecule, right? The atomic mass of carbon and oxygen to measure the atomic weight, right? To calculate the atomic weight, correct?
Exactly. So that's something that you can do very easily. Look up the atomic table, the periodic table, and take a look at it. So you could solve that problem yourself.
Well, thank you so much, Robert. That was so cool and such a great way to end our experiments for National Chemistry Week. That was so exciting. I was so intrigued. So thank you so much.
Absolutely. Yeah. And our website, again, if you want to put that into the chat, it's databot.us.com. And all those experiments are in the lessons area. So people could actually create their own cave of dogs at home if they want to give it a try.
Yeah, well, thank you so much. We did put those in the chat, as well as that tool you gave us, Fox, because that seems like pretty cool. Yeah,
that's a fun one. And everybody can do that at home. It's free. It's an amazing tool. There's a lot of lessons online for it as well.
Okay. Well, thank you so much, Robert, and enjoy the rest of your day.
Thanks for having me. Bye.
Bye. So, in order to be respectful of your time, we're not going to do another Jeopardy game, but we are going to announce the winner of our giveaway. So we said the winner of our giveaway would be a person that was so interactive in the chat, and many of you were interactive, so it was really close, but our winner is actually Zara, I'm sorry, it makes me pronouncing it, Zara Patrick. And you actually won a $40 gift certificate to my gym center to actually get a STEM kit and or STEM notebooks from my STEM kits. I'm sorry, my gym center. So, Zaria, I'm going to send you a private message where you can email me and get a chance to get your prize. And so, everyone, I just want to thank you so much for sharing National Chemistry Week with us. I hope that you had a great time and learned so much from our speakers that gave our great demos. And many of them you could do on your own. That's STEM Assist, Kids for Chemistry, Databot, and then the cool thing that Dr. Campbell gave us about national chemistry. About the chemistry of fireworks. So enjoy the rest of your day. And if you want to review it again, you can also always look at our YouTube channel. So thank you so much for joining us for our Chemistry Week celebration, and have a great rest of your day.